Don't spend hours and hours and hours on it. The stuff we're going to do today is much more important. All right? Energy flow and chemical reactions. We'll get this out of the way first. Exergonic and endergonic. How many of you guys have heard of exothermic reaction? What's an exothermic reaction do? Gives off energy, releases energy. Same thing with exergonic. These are just weird ways to say exothermic and endothermic. Exergonic reactions give off energy. Exergonic reactions give off energy. Endergonic reactions require energy. Endergonic reactions require energy. So we can say decomposition reactions are exergonic. Decomposition reactions are exergonic. Synthesis reactions are endergonic. Synthesis reactions are endergonic. Make sense? Everybody's okay? All right, now biochemistry. Again, this is the important part. Biochemistry. We are biochemistry. We are made of mostly organic compounds. Mostly organic compounds. Organic compounds contain carbon and are held together with covalent bonds. Organic compounds contain carbon and are held together with covalent bonds. Covalent bonds. Those are organic chemicals. Anything else is inorganic. Anything else is inorganic. We have inorganic stuff in our bodies. Totally. Salt, sodium ion, chloride ion, all that stuff, inorganic. But the big molecules, the really important ones, are organic. Talk about proteins and lipids and DNA, nucleic acids, all that stuff are organic molecules. Everybody all right? Water, of course, is inorganic as well. Water is really important. Water has special properties that let it do so many different tricks. Water, without water, there's no life, pretty much, period, as far as we know. Without water, we can't see how life would work. One of the things water does really well is dissolve things. It is held together with polar covalent bonds, and it dissolves a lot of stuff. If something is ionic, it dissolves in water. If something is held together with polar covalent bonds, it dissolves in water. Pretty much the only thing that doesn't, the only things that don't dissolve in water are things held together with non-polar covalent bonds. They even call water the universal solvent. Water dissolves so many things. Does water dissolve oil? No, oil floats on top of water. You know that because you see the Italian dressing with like the vinegar and the oil, right? You shake them up and they mix up, but they separate again. So oil is held together with what kind of bonds? Non-polar covalent bonds. I want you to write this down with parentheses and stars. Like dissolves like. Like dissolves like. Polar things dissolve polar things. Non-polar things dissolve non-polar things. And don't forget, there's also ionic in there too. So if I had a glass of water, will salt dissolve in there? Salt dissolves in water, right? Salt held together with ionic bonds. Will sugar dissolve in water? Yes. So what kind of bonds hold sugars together?
Polar.
Polar covalent. Polar covalent. Sugar is also held together with polar covalent bonds. Sugar and salt both dissolve in water. Most things held together with polar covalent bonds dissolve in water. Let's try some non-polar things. Does styrofoam dissolve in water? No. So what kind of bonds hold styrofoam together? Non-polar covalent. Does styrofoam dissolve in gasoline?
Yes.
Yes, it does. If you're run out of gasoline, go stop by the AM/PM Quickie Mart and get a styrofoam cup and try to bring gasoline to your car, because it will eat the styrofoam. And if you want TSA to come to your house, get some gasoline and dissolve enough styrofoam cups in it until it starts to get sticky, then add some Tide and you have made napalm. And they will come and they will arrest you and they will put you in a cage. So don't do that. Non-polar things dissolve non-polar things. Polar things dissolve polar things. Water also participates in chemical reactions. We're going to see that in just a minute. Water participates in chemical reactions. You can actually break water apart and use it to help make reactions happen. There's a very fancy pair of reactions further down the page. It says dehydration, synthesis, and hydrolysis. This is what I mean by participates in chemical reactions. I want you guys to really know dehydration, synthesis, and hydrolysis when you get there. It's important. When I say it's important, what does that mean? Yeah, be on test or quiz. Water has a high heat capacity. Water has a high heat capacity. It also has a high heat of vaporization. That means it takes a lot of energy to raise the temperature of water. It takes a lot of energy to raise the temperature of water. And it takes a lot of energy to get water to evaporate. It takes a lot of energy to get water to evaporate. That's why water is good at cooling us. That's why we sweat. Because that water evaporates off of us. Now down here in Florida, sometimes it doesn't evaporate very well. We get pretty sweaty. When the humidity is 90% outside and it's 90 degrees, we still get pretty wet. When you guys been in the desert, it's hot. You get all sweaty and stuff, it really evaporates pretty quick. You get a little salty, but it evaporates pretty quick. That helps cool us. Water also serves as a lubricant and a cushion. Water also serves as a lubricant and a cushion. Anywhere stuff moves together, moves against each other, you'll find water. Our synovial joints, all the joints in our hands, arms, legs, wherever, neck, anything, has synovial fluid in the joint. It's mostly water. There's some stuff in there to make it slippery too, but it's mostly water. Water also helps our organs move against each other. Remember we talked about the visceral and parietal pericardium? Where do we find the visceral and parietal pericardium? Around what?
Heart.
Around the heart. We talked about how that prevents friction, prevents the heart from rubbing, right? It's mostly water. Serous fluid is mostly water. So water serves as a lubricant. It also serves as a cushion. It gives us some mass and stuff to move when we have impacts on our body. Everybody all right? Salts. Salts are also inorganic. Salts, when you put them in water, turn into cations and anions. They dissolve and form cations and anions. What is a cation?
Is it positive?
Yeah, positively charged particle. A cation is a positively charged particle. An anion is a negatively charged particle. You put a salt in water, it falls apart. Positively charged and negatively charged particles. Now, acids and bases. Acids and bases are a lot like salts. Acids and bases are a lot like salts. Except when an acid dissolves in water, it gives off a hydrogen ion. It gives off a hydrogen ion. The hydrogen ion is a cation. Hydrogen ion is a cation. Very common acid. What acid is this? Hydrochloric acid. Hydrochloric acid in a beaker falls apart. H plus Cl minus. So we can see the cation here is hydrogen. Does that make sense to you guys? If the cation is hydrogen, it's an acid. There's another way to say that. It might not make a whole lot of sense at first. Now let's take a look over here. There's hydrogen. How many protons does hydrogen have? One. How many electrons does it have if it wants to be uncharged? One. Got one plus and one minus. You take that electron away, you're left with H plus. That's why we also say acids are proton donors. Because a hydrogen nucleus is a proton, that's all there is. You'll see in books all over the place, acids are proton donors. That means they give hydrogens, they give protons. Acids give hydrogens, give protons. Does that make sense to you guys? This thing here, this hydrochloric acid, is giving up protons, hydrogen plus. Everybody okay? Now bases are kind of the opposite. Bases, when they dissolve in water, give off hydroxide ion. Anybody know what that is? Ever get a face full of easy off oven cleaner? Nobody cleans ovens anymore. But that's sodium hydroxide. That is a strong base. Sodium hydroxide. When you put that in a beaker of water, it falls apart. Like this. Its anion is hydroxide. OH minus is hydroxide. It falls apart to that. What would happen if you put your face in a bowl of hydrochloric acid? It would burn it. Yeah, that's not good. That's not good. Which would you rather put your face in, a bowl of hydrochloric acid or a bowl of sodium hydroxide? Two bowls right here, make your choice. Sodium hydroxide. The correct answer is neither. Because sodium hydroxide will melt your face too. Yeah. They use sodium hydroxide to have this new way to get rid of a body legally. Instead of having your body cremated, they put it in hot, soapy water with lots of sodium hydroxide. It just dissolves it and goes down the drain. You don't have to use the energy to burn the body. You don't have to waste ground plunking the bodies in the dirt. Just goes away. Gone. Sodium hydroxide is not something you wouldn't put your face in either, because it will do it. The hydrogens tear apart the molecules of your face. The hydroxides tear apart the molecules of your face. Neither one of them is very good. So there they are. Now, if I add hydrochloric acid and sodium hydroxide together and drink it, what happens to me? Nothing. Because what I've made is salt water. Because HCl plus NaOH is going to yield HCl plus H2O. These H's get together with the OH. It makes H2O. And the sodium and the chloride stay dissolved in their ionic form. And you get salt water, you can drink it. If you're going to try that at home, make sure you're really good at measuring, because you don't want to have too much of one or the other. And if you've actually had a real chemistry class, you know you do not mix strong acids and strong bases together, because that reaction can be, as they say, vigorous. Like, so, but you get the idea, right? Acids and bases. There's a way to measure acids and bases. pH. You guys have all seen pH before, right? Little p, big H, pH. What pH is a measure of is how many hydrogen ions there are in what you're measuring. How many hydrogen ions are available. Like this, in whatever you're measuring. There can be a whole bunch, in which case you have an acid, or there can be hardly any at all, in which case you have a base. Does that make sense to everybody? Let's take a look at a pH scale here real quick. Take a look at page 40. There's a pH scale. pH runs from 0 to 14. pH runs from 0 to 14, and that's a measure of how many hydrogen ions there are. And if you look at the concentration on that picture on page 40, down at the very bottom, it says pH 0. That's straight out acid. There's a whole bunch of hydrogen ions and not very many hydroxide ions. 10 to the minus 14th, very few hydroxide ions, and a boatload of hydrogen ions. If you go up to the middle, see it says pH 7, neutral. The OH minuses and H pluses are equal in number. So when they're equal, what do? They make water. They both join up because opposites attract, plus and minus, they both join up. Pure water is pH 7, it's neutral. And then up at the top, pH 14, it has a whole bunch of OH minuses, hydroxides, and hardly any hydrogens. So, burn your face off, everything's cool, burn your face off. That make sense? Now let's take a look at some of the common things you might run across. Oven cleaner or lye clocks in a pH 13 or even a little more. Anybody make soap? Use lye? No? Okay. Ammonia is about pH 10 or 11. Bleach, pH 9.5. Egg whites are about pH 8. Do egg whites burn you? No. pH 8 is fine. Blood, pH. It says 7.4 in the book. I want you to write this down and know this. I don't ask you to remember many numbers. Normal blood pH is between 7.35 and 7.45. You own a human body, you should know some things about it. That's one of them. The normal blood pH should be between 7.35 and 7.45. Is that acidic, basic, or neutral? basic, it's above 7. Just a little bit above 7. But it's not alkaline, or basic pH. And then we get down into the acidic stuff. Coffee, about pH 5. Wine, pH 2.5 to 3.5. Lemon juice, gastric juice, about pH 2. Coca-Cola's down there somewhere too. I forget off the top of my head what pH is of Coca-Cola, but it's pretty acidic. And you can take nails and put them in iron nails and put them in Coke to dissolve. Yeah. Gastric juice, pH 2. What's gastric juice? Stomach acid. Stomach acid can be even a little bit below pH 2. It's pretty fierce stuff. It'll eat the paint off your car. So if you're driving your drunk idiot friend home, and they hang their head out the window and throw up, and it makes a big stripe back over the top of your car, and you don't clean it up for a couple days, it'll mess your paint up. That's me how I know that. pH 1, all the way down to acid. Any questions, everybody okay? By the way, this is neutralization. You take a strong acid and a strong base and put it together, neutralize. All the pluses hook up, all the H pluses hook up with all the OH minuses, and you get water. That's what neutralization means. Buffers are things that we're going to talk about for the next 2 semesters. But for right now, just know buffers prevent large swings in pH. Buffers prevent large swings in pH. That's a carbonic acid. Go ahead and write that down. I'm not going to quiz or test you on it just yet. That's more for AP2. But that's an important acid. That's a weak acid. Weak acid means it doesn't fall all the way apart in water. These guys are strong acids and strong bases. They totally dissociate. They fall all the way apart in water. Carbonic acid doesn't. Some of it falls apart, some of it doesn't. So what happens if you add acid to carbonic acid? It doesn't get, the pH doesn't drop as much. It kind of hangs out a little while. You can put some acid in there and the pH isn't going to change much. You can put some base in there and the pH isn't going to change much. That's what makes it a buffer. You can add some acid or add some base and the pH isn't going to change a whole lot. With pure water, a little bit of acid changes the pH a ton. So with buffers, a little bit of acid, a little bit of base doesn't change the pH very much. That's why we say buffers prevent large swings in pH. Your blood pH is pretty narrow, right? 7.35 to 7.45. It has to be in that area. If your blood pH gets down into like 7 or even below 7, or if it gets 7.6, 7.7, you are in deep trouble. You might die over a small change. So your blood has buffers in it to keep from doing that. Does that make sense to you guys? Just remember, buffers prevent large swings. We'll talk about all that stuff probably in the institute. Organic compounds. This is the important stuff. First of all, here's a nice little quick summary. pH, acid buffer. Some of you guys are looking at videos on YouTube. Good job, keep it up. The rest of you, great resource. Stay away from the weird ones.
When water dissociates, it breaks apart into an equal number of hydrogen ions and hydroxide ions. In contrast, when other substances dissociate, they may release more hydrogen ions or more hydroxide ions. For example, hydrochloric acid releases more hydrogen ions as it dissociates, and sodium hydroxide releases more hydroxide ions. Depending on its concentration of hydrogen ions versus hydroxide ions, a substance can be classified as either an acid or a base. The pH scale measures how acidic or how basic a substance is. It ranges from 0 to 14, with 7 being neutral. When a substance has a pH of 7, like water does, it releases an equal concentration of hydrogen and hydroxide ions. When a substance has a pH of greater than 7, it's classified as a base and releases a greater concentration of hydroxide ions. The more hydroxide ions that are released, the more basic the substance is. Bases tend to feel slippery and are often used as household cleaners. Milk of magnesia and ammonia are both common bases. When a substance has a pH of less than 7, it's classified as an acid and releases a greater concentration of hydrogen ions. The more hydrogen ions that are released, the more acidic the substance. Acids tend to taste sour. Lemon juice, stomach acid, and coffee are all examples of acids.
Make sense? I also wanted to show you this. Penguin Prof has some pretty good videos. I'm not going to burn 10 minutes or 13 minutes, 18 minutes or 13 minutes showing you this. But if you want to look at this stuff, Penguin Prof, basic chemistry Penguin Prof is what I searched for. Those will give you a little more in depth than what I talked about. But how many of you guys have to understand everything before you understand anything? Alright, yeah, that's totally cool. It happens. It's the way it is. That's good. Use this stuff, okay? Some of it I gloss over in class. Do this stuff, and also come visit me in the Learning Support Center if you got questions. I've been there the Wednesdays after lab, last couple weeks. I'll be there again. So if you have questions, come see me, okay? All good with inorganic compounds. All right, organic compounds. Here's our pair of reactions. These are really, really, really important reactions. Really, really, really important. They are dehydration synthesis and hydrolysis. Dehydration synthesis and hydrolysis. Let me preface this by saying a lot of organic molecules are really big. A lot of organic molecules are really big. These reactions build up or break down organic molecules. These reactions, dehydration synthesis, and hydrolysis, build up or break down organic molecules. Take a wild guess and tell me which one builds up organic molecules. Dehydration synthesis, how do you know? It says synthesis in the name. Synthesis is to build something, right? Without knowing anything about the reaction, tell me something else about what's going on during dehydration synthesis. Yeah, you're removing a water. You are removing a water and you're building something with dehydration synthesis. Now the other one, hydrolysis. Let me give you a word, lysis, L-Y-S-I-S. It's in hydrolysis. Lysis means to cut something or to break something. Lysis means to cut something or to break something. So in hydrolysis reactions, I'm breaking molecules apart. And I'm using water to do it. Hydrolysis reactions, I'm breaking something apart. And I'm using water to do it. Remember we said water participates in chemical reactions? This is how it does it. We either form a water or we break a water apart. And rather than try to explain these, I'll show you how they work. Are you guys okay with me showing you little videos and stuff like that? How many people like it? Okay. I kind of thought that's the way it was. It usually is.
Many important biological molecules are made of repeating subunits called monomers. When many monomers join, the result is a polymer. For example,
You guys got all that, right? A polymer is a long chain of the same molecule over and over and over and over again. How many of you guys have heard of polyester? How many of you have polyester on right now? I'm all cotton baloney. You got some polyester somewhere. There's a blend somewhere you wear. Polyester means a lot of esters all hooked together. It's plastic. Where would we be without plastic? Repeating molecules over and over and over again. The basic molecules, a monomer, bunch of them chained together is a polymer. Everybody okay with those terms?
simple. Amino acid monomers join to form a protein polymer. And glucose monomers combine to form a complex carbohydrate polymer. Biological polymers form by dehydration synthesis reactions. As you can see here, each of the monomers in this reaction has a hydrogen, or H, and a hydroxyl, or OH group.
Okay. Open up your books if they're not open already and turn to page 42, please. There is an equally uninspiring drawing for an uninspiring video, but they match up nicely. Got an H and an OH. Those are the chemicals that are going to participate in this reaction. Dehydration synthesis. Dehydration, I'm going to remove a water and make something.
In the course of the reaction, the hydrogen is removed from one monomer and the hydroxyl group from the other. The hydrogen and hydroxyl group combine to form water, and a bond links the two monomers.
See, when you take an OH off one side of an H off the other side, that bond, that sticky end, is still there. There's still something that wants to share electrons with something else. These are covalent bonds, right? So they're going to be sharing electrons. We don't know if they're polar or non-polar yet, but we know they're covalent. So when you take off an OH, that wants some electron sharing. When you take off an H, that wants some electron sharing. When you take this out of the middle, now they're sharing electrons with each other. So they're bonded. Does that make sense to you guys? Any questions? This could be touchy. You're all right?
Hydrolysis is the opposite of a dehydration synthesis reaction. During a hydrolysis reaction, a polymer is reduced to its monomer subunits by the addition of water. In fact, the word hydrolysis literally means to break water. The hydroxyl group from a water molecule attaches to one monomer, and the remaining hydrogen attaches to the other monomer. In other words, water is used to break the bond holding monomers together. Let's do a quick recap. During dehydration synthesis, monomers join to form polymers, and water is released. The opposite happens during hydrolysis, where water is added to the reaction to break a polymer into monomers.
Make sense? Everybody okay? Who totally gets it? It's like, I can get it if I watch the video a couple more times. It's like, what the heck just happened? Seriously, what the heck just happened? How can I help you?
I'm just not grasping any of it, honestly.
Okay. You try something. Molecule A, molecule B, doesn't matter what they are. You good? This dude has some OH sticking out, part of the molecule. This dude has a hydrogen sticking out, part of the molecule. Is that okay? Let's say I want to join this together and make an AB molecule. Both of them stuck together. The way I do that is I grab this OH, I grab this H, I pluck them both out. There's actually protein that does that. Imagine a machine that comes along and goes, plucks that grape and plucks that grape. So now I got the H and the OH. The H and the OH want to be together because they're opposites. Remember the H pluses and the OH minuses? They're opposite charges, so they want to stick together. So they're going to go up here and make water because there's two hydrogens and one oxygen. So they're making water. You good? Now, I got rid of that OH and the H and they're gone. But there's two sticky parts left where I took the OH off of one, I took the H off the other. There's like a sticky part there. It wants to be stuck to something. So what better place to stick it than the other molecule? Because there are two sticky ends, right, wanting to be bound with something. Let's stick them together. So now I got AB. I took the water out. Did that help at all?
Wow.
Okay. Good. Anybody else? Go ahead.
So hydrolysis is a problem to a monomer, and then it's vice versa.
Yeah. Hydrolysis breaks them apart. See, everybody in the class is glad you asked that question because they're all thinking the same thing. Thank you for asking that question. So is this a little better for most of you all? And the opposite would be, I got AB, and I want to chop it apart, right? So, I got a water, and I got my AB molecule. There's another protein, actually sometimes it's even the same protein, that is going to break this bond. Boom, broken. Now I got two sticky ends. I got to put something there, otherwise they're going to react with something else. So I can take a water and I can split it into H and OH, and I don't remember which way I had it before, it doesn't matter. The H plus I can stick on here, and the OH I can stick on there. And now A's all happy because it doesn't have any sticky ends, and B's all happy because it doesn't have any sticky ends. And I'm back to this. Two separate molecules. That's hydrolysis. Breaking them apart is hydrolysis. Sticking them together is dehydration synthesis. How do you feel about that? A little better maybe? Anybody still not sure? Alright. Dehydration synthesis and hydrolysis. And of course, if you Google dehydration synthesis and hydrolysis, there's tons of other videos. Too much. How many guys have found Crash Course? Biology, chemistry, yeah. Awesome. I'll tell you some Crash Course as we go along. How many guys use Khan Academy? Khan Academy is pretty good. It goes into way more detail than we need, especially in the chemistry group. If you want to, they have to understand everything before I understand anything. Check that out, see if that helps. So we all good? Dehydration, synthesis, hydrolysis. Learn it, live it, know it. You need it. Since we're on page 42 and 43, we can start talking about chemistry. If you look at page 42, there was our dehydration, synthesis, and hydrolysis kind of mock-up or model. And then look at the bottom. There's an example reaction. Glucose and fructose, put them together and you have sucrose. All of these molecules that we're going to talk about, you build them with dehydration, synthesis, you tear them apart with hydrolysis. Over and over and over again. Build them with dehydration, tear them apart with hydrolysis. All of these organic molecules, the next 4 categories we're going to look at, all held together that way. If you don't understand it, at least write it in your notes. All of these organic molecules are assembled and disassembled with dehydration, synthesis, and hydrolysis. All of them. Rarely will you hear me say all, none, everything, nothing. This is the case. All right? So we're going to start off with carbohydrates. Carbohydrates are big in the news, blah, blah, high carb, low carb, oh my gosh, here's a carb. Well, carbohydrates is a fancy way of saying sugars. But there are other molecules too, other than sugars, that are carbohydrates. Carbohydrates contain carbon, hydrogen, and oxygen. Carbohydrates contain carbon, hydrogen, oxygen. And if we wanted to be really fancy, we could talk about a ring structure too. You look in the bottom of page 42, you see things that look like this. Ring structures. Carbohydrates we're going to be dealing with are usually in ring structures. So if you want to say, this is A, and that's B, see how these guys look alike? That's exactly what we did. On the bottom of page 42, we took this and stuck them together. Well, this is glucose and this is fructose. And we stick them together with dehydration synthesis, and we get sucrose. How many guys ate some sucrose this morning? What am I talking about? What's sucrose? Table sugar, yeah! Little white Dixie crystals. Sucrose is table sugar. It's 2 rings. A glucose and a fructose. Glucose and fructose are also sugars. You guys heard of high fructose corn syrup? You eat it every day, unless you're really paying attention, because they sneak it in on you. The stuff you wouldn't think has a lot of sugar in it is high fructose corn syrup, unless you buy the special ones that cost more money. Fructose. Carbohydrates provide fuel for the body. Carbohydrates provide easily available fuel for the body. Easily available fuel for the body. Carbohydrates also form the backbone of DNA. Carbohydrates also form the backbone of DNA. Carbohydrates also serve as cell surface markers. Carbohydrates also serve as cell surface markers. what's a cell surface marker? Where is it? Go ahead and say it. It's on the surface of the cell. Yeah, it's something that's on the outside of a cell. It's actually like an ID card. Your body's very picky about what it lets inside. Part of you belongs. Anything that's foreign doesn't belong. The way your body checks that is by the carbohydrates on the outside of the cell. So it's like your ID card says, yep, I'm good, I'm here, let me in. Your bus pass, your student ID, your driver's license, something like that. It says, hey, I belong. Please don't kill the immune system. If you don't have the right carbohydrates on the outside of yourself, you are marked for death. The body's immune system will kill you. Because you're an outsider, you're a foreigner, you're an invader. You might damage the body. So these carbohydrates serve as cell surface markers to let the body know, hey, it's cool, I belong here. I'm part of the gang. Now, there are monosaccharides, disaccharides, and polysaccharides. Monosaccharides are one ring. Monosaccharides have one ring. And if you look on page 43, there you'll see glucose, fructose, galactose, deoxyribose, and ribose. Those are just variations of sugar ring. There's no, I'm not going to ask you any specific functions. What's the function of fructose compared to galactose? I'm not going to ask you that. Don't worry about it. It's a single ring, so it's a monosaccharide. Mono means one, saccharide means ring. Y'all good? Take a wild guess. Tell me what a disaccharide is. Two rings. Disaccharides are two rings. Now, there's a couple there. We already talked about sucrose is disaccharide. There's two rings there. Sucrose is table sugar. How many guys like Mexican Coke better than regular Coke? Oh yeah. Far superior. You know why? Cane sugar instead of high fructose corn syrup. How many guys think you can taste the difference between regular sugar and high fructose corn syrup? You can either buy the Mexican Coke for like $6 a six-pack, or if you're really sneaky, you wait till Passover, and you find the 2-liter bottles with the yellow caps on that are Passover, that are approved for Passover, because during Passover you can't have grain. Fructose corn syrup comes from corn, so it's grain. So they put, Coca-Cola puts real sugar in those bottles. So it's only in stores during Passover. It's got yellow caps. It's only in 2-liter bottles. I'm a bit of a Coke head, Coca-Cola head. So when I see those in the store, I'll buy like 2 or 3 and save them and mix them with Jack Daniels. Life is good. But you can kind of tell the difference. Try a little blind taste test. That's a blind taste test. So I don't know how to explain it. For me, sucrose, cane sugar, tastes rounder. It's not a sweet, that's sweet product. It's like a not just fierce sweet. And of course, if you listen to the sweetener companies, oh, high fructose corn syrup is fine. It's the same stuff in sugar. The reason they use it is it's cheaper. It comes in liquid form rather than white crystals. But might be doing funny things to your metabolism because there's extra fructose there. Fructose gets converted to glucose in the liver, and your body thinks, oh my God, I have all this sugar, and makes all the insulin, and you get diabetes. Which the food companies won't tell you this, but other people say maybe that's one of the reasons why we have the obesity epidemic and we have the diabetes epidemic and all that stuff, because we switched from regular sugar to corn, like fructose corn syrup. So that's a debate for another time. Make sure you're well informed, get lots of sources, whatever. But something to think about. You might want to try to avoid it even. Maltose is a disaccharide with 2 glucoses linked together. Maltose is a disaccharide. It's just 2 glucoses. It's all glucose. Where do you think maltose comes from? Maltose comes from grain. tasty malt beverages. We use grains, wheat, corn, rye. Your Budweiser, you use rice. Not a big fan of Budweiser. But you break down those maltose, the yeast eat the maltose, break it apart into glucose, and literally poop ethyl alcohol. If you like to drink booze, that's yeast poop. It really is. Maltose. Lactose, where do we get lactose from? Milk, dairy products. And if you're lactose intolerant, what happens if you eat lactose? Bad news, yes. Intestinal discomfort. Increased flatulence. Maybe even a little skinny booze. All of those are disaccharides. Now flip to page 44, polysaccharides. Polysaccharides are also really important molecules. Two categories, starch and glycogen. Starch is found in plants. Starch stores carbohydrates. Starch stores carbohydrates. Potatoes are the ultimate starchy vegetable, right? Big giant balls of starch. That's just sugar. Potato plant gets sunlight, uses sunlight to convert blah, 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 carbon, blah, 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 all this stuff, and end up with starch. Big bag of sugar. Tasty French fries. Glycogen is animal starch. We don't make starch. We make glycogen. Glycogen is how we store glucose. If we have too much glucose floating around in our blood, what happens? We got diabetes and blood sugar levels in the 200s and 300s and bad. So we have to store it packed away as glycogen. We store it packed away as glycogen. Glycogen is how we store glucose, like the potato stores glucose with starch. Glycogen is an important word for you guys. It's an important concept. Everybody okay? By the way, carbohydrates are polar in nature. They're held together with polar covalent bonds. So what does that mean to us? We know they're polar covalent, so they dissolve in water, yes. Carbohydrates will dissolve in water. Lipids, on the other hand, are nonpolar. Lipids, on the other hand, are nonpolar. Lipids are fats. Lipids are basically liquid at room temperature. Lipids are fats. There are a couple different types of fats. Triglycerides are also called neutral fats. It's called triglycerides because it has 3 chains. It has 3 chains of fatty acids. All hooked to a glycerol. Take a look at page 45. This is a nice easy way to draw carbohydrates. That's the monosaccharide. I got to chain them together. That's the polysaccharide, right? I should use that. Take the extra 20 seconds to do it right. Polysaccharide, right? Monosaccharide, polysaccharide. When I draw triglycerides, I do it like this. I'm leaving out a lot of chemical structure, but you can see the three tails of fatty acids, right? Three tails of fatty acids. That tells me it's a triglyceride. Page 45, you can see triglycerides. Triglycerides can either be saturated or unsaturated. Saturated means every single carbon on there is bound to as many hydrogens as it can hold. That means every single carbon on there is bound to as many hydrogens as it can hold. Unsaturated fats means you're missing some hydrogen. Unsaturated fats means you're missing some hydrogen. Because those hydrogens are missing, carbons form double bonds with each other. Carbons form double bonds with each other. It makes the legs a little kinky. They get bent, and they have double bonds in them. On that page, those are saturated fats. And if you look over on page 46, you'll see an unsaturated fat. So when they say monounsaturated fat, that means there's one double bond. When they say polyunsaturated fats, there's more than one double bond, right? Which is better for you, saturated fat or unsaturated fat? Unsaturated fat, yeah. Unsaturated plant. Yeah, unsaturated fats come from plants. Saturated fats come from animals. So you should eat more plant fat than you should animal fat. It sucks because bacon is good.
Avocados are good too.
Yeah, absolutely. Olive oil is good too, and that is unsaturated. Any Costco heads in here? You get their organic extra virgin olive oil. Yeah, that's a real thing. Yeah, that's not like the store crap. You know, they say virgin olive, extra virgin olive oil in the stores. Most of those are crap. They're Costco. I'll try not to preach. And the Costco head. All right, those are triglycerides. Phospholipids. Phospholipids are probably the most important lipid we're going to take a look at. Because phospholipids make up the cell membrane. Phospholipids make up cell membrane. If you look on page 46, you can see a phospholipid there. Phospholipid's a funny molecule. And this is how I draw it. Got a head and two tails. Got a head and two tails. This is a phosphate group. And these are fatty acids. So chemically, this end is polar. And this end is nonpolar. Phosphate end is polar. It wants to dissolve in water. Fatty acid end is nonpolar. It does not want to dissolve in water. We have some fancy names for this. We say the phosphate group is hydrophilic. Phosphate group is hydrophilic. What does hydrophilic mean? Loves water. almost. The fatty acid nonpolar end is hydrophobic. Fatty acid nonpolar end is hydrophobic. What's hydrophobic mean? Hates water, yes. SOW, scared of water. And that makes for weird molecules when you put them in water. By the way, there's a fancy word for molecules that have a polar end and a non-polar end. We call them amphipathic. We call them amphipathic. A-M-P-H-I-P-A-T-H-I-C. Amphipathic. Because these guys are amphipathic, polar, non-polar, they form the cell membrane. Phospholipids form the cell membrane, and that's really important. Phospholipids form the cell membrane. Because some of them want to be near acid. Some of them want to be near water. Some of them want to be far away from water. So when you put them in water, this is what they do. They form little beads like this. So you got water on the outside. So these guys are happy because they're near water. And these ends are happy because they're near each other. They're around other fats. They make little blobs. If we're talking about soap, that's where the greasy dirt is. That's why soap takes greasy dirt out of your clothes. Because the grease dissolves in the fatty part and the outside dissolves in the water part and washes it out of your clothes. In a body cell, you end up something like this. Now you guys are going to have to give me 1 second, right? Do all this. You end up with 2 layers. And all the little tails are in that layer. And there's water out here and water in here. And end up with a ball with a phospholipid bilayer. But there's 2 layers of it. That's what a cell is. A cell has like a nucleus in here and a little mitochondria and some other stuff. And a water environment on the inside, then there's a cell membrane, and then there's water environment on the outside. That's why phospholipids are hugely important to us, because they make up all of our cells. How I feel, okay? Steroids. Steroids are actually made from cholesterol. You all heard cholesterol is bad, right? Not so much. Cholesterol is a pretty good thing because cholesterol is what we start with when we want to make sex hormones. Without cholesterol, there's no sex hormones. Steroids, like testosterone, made of cholesterol. Eicosanoids, that's a fancy word. Eicosanoids know this. Eicosanoids make things called prostaglandins. Eicosanoids are lipids that make things called prostaglandins. Prostaglandins are important because they help us clot our blood. Prostaglandins help us clot our blood. They also cause inflammation. They also cause inflammation. Now, I want to show you this. We don't have enough time to get too far into this. Best thing to do is talk a little bit about proteins. Proteins are long chains of amino acids. Proteins are long chains of amino acids. There are 20 different amino acids that make up all the proteins in our body. There are 20 different amino acids that make up all of the proteins in our body. If you want to see a list of all of the proteins, page 103 in your book, all the amino acids, page 103 in our book, alanine, arginine, asparagine, aspartic acid, cysteine, glutamic acid, glutamine, glycine, histamine, isoleucine, and more. Don't memorize those. I was reading the list. Alright, but if you want to see what all 20 amino acids look, well, not what they look like, but their names, on page 103. What I want you to know is protein is a long chain of amino acids. Between now and Wednesday, I want you guys to watch this video, What is a Protein? And you're going to find this by going to YouTube, put in What is a Protein, and put in RCSB Protein Data Bank. That'll bring you right to that video, RCSB Protein Data Bank. Turn the light off, make it a little easier for you to see. RCSB Protein Data Bank. What is a protein? If you just put in what is a protein, you'll probably get it on the first page. Put RCSB or something, or protein data bank, or you probably don't have to write the whole thing up to get it on the first page. Alright, this is going to be important. Now in the last minute, I'm going to reinforce something else that you should know. A peptide bond is a fancy name for covalent bonds. Let's get more specific. A peptide bond is a fancy name for a polar covalent bond that sticks two amino acids together. A peptide bond is a fancy name for a polar covalent bond. So is this going to dissolve in water? Yes. Polar covalent bond that joins two amino acids together. That is a peptide bond. That is a peptide bond. Questions, comments, concerns? How are we feeling? Everybody okay? You gonna have a quiz on Wednesday? Yes, what's it gonna cover? Everything since the last quiz, both Wednesday and today. I might ask you a fun question to see if you paid attention. And for those of you who came in late, I'm going to spring a Monday quiz pretty soon. Make sure you're not slacking off on Mondays and get here on time on Wednesday. And you'll miss it. Why be free?